Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosine River College in Sacramento, California. This video is for trig students, your first time through trig, or if maybe you're reviewing trigonometry and perhaps you've forgotten how to graph trig functions, which is very common. And so prior to this video, you should have a strong understanding of trig functions, how to evaluate trig functions, things like reference angles, all the special angles for trig functions, the Pythagorean identities, cofunctions, all that fun stuff. So that's all down before you even begin this video. Now we enter into what would normally be like the second major unit of material within a trigonometry course, which is graphing the trig functions. And we're going to start with just the sine and cosine for quite a while here. Mainly because actually those are the easiest to graph. Also, they are the most popular to graph. They're the most important to graph. So let's see. Let's go ahead and make a table of values for the sine and cosine functions, and then we're going to estimate these sine and cosine functions graphs. And this is going to be an estimate of the base graphs for the trig functions sine and cosine. Now I have a habit of starting with the sine function just because I like the sine function. So we're going to start with the sine function here. A couple things I need to note. One thing, up to this point, you've dealt with sine of t when t is the length of the arc along the unit circle, or sine of theta when theta is an angle. But when we go to graph, we are so used to graphing on an XY axis or Cartesian coordinate system that our inputs are just easier if we say, let our inputs be X. They don't have to be. You could call this f of theta equals sine of theta. That's perfectly fine. But it's just much easier, I think, for students to understand it if we just leave the input as an X. So that is just a heads up. This is not the same X as the X in the definition for the trig functions. And what I'm referring to there is that sine of t is defined to be the y value on the unit circle, and cosine of t is defined to be the x value on the unit circle. That is if you're on the unit circle, but now I'm just saying in general, we're just plugging in a value. It's an angle, and we're going to call that x instead of theta. So don't let those letters fool you or confuse you. All right, let's build a table of values, and I'll just do it by pausing. Now, when you graph trig functions, you will always graph them in radians, not degrees. So again, this kind of goes along with the theme that I've been trying to drive home, which is that we're going to let go of the degree. We'll come back to it every once in a while for certain applications, let's say in engineering or something like that. But for the most part, you're going to be working in radians from this point forward. Let's talk about radian angles that are increasingly popular for us. So let's actually look at the axial angles first. So what I'm going to do is leave a little space in here. The axial or quadrantal angles are 0 radians, pi over 2 radians, right there. I'll leave a little space here, and we'll also do pi radians. That's 180 degrees. We'll leave a little space for another value if we need one. And then 3 pi over 2 radians. That'd be 270 degrees. Leave a little space. And then 2 pi radians. Now, the reason why I'm only going to 2 pi, I could go much further than that, honestly. But I'm only going to 2 pi because we know that the trig functions are based on the unit circle. And if you think about the unit circle and the sine function itself, the sine will return the y values on the unit circle. And by the time we get all the way back around to 2 pi, those values are just going to repeat. So there's no need to really list out anything other than from 0 to 2 pi for right now. So let's see, the sine of 0 radians, well, that would be if you're on the unit circle, which I should have kept, and you're facing the angle of 0 radians. So let's go ahead and mark that. That's this point right here. Well, remember, sine returns the y value, and so that would be a y value of 0. If you're facing an angle of pi over 2, which is way up here, you're at the point 0, 1 on the unit circle, and its y value is 1. If you're facing an angle of pi, you're way over here, and you're at negative 1, 0, so your y value is again 0. If you are at 3 pi over 2, which for some reason I didn't point an arrow at, you're at 0, negative 1, so the y value is negative 1. And then again, if you're at 2 pi, you're just basically facing back at the angle 0, so your y value is 0 again. All right, so that being done, I'm just going to erase these little arrows here because I forget why I put them in there. Let's go ahead and fill in some other points because that looks pretty sparse. 0, 1, 0, negative 1, 0. Let's fill in some other spots here. So let's say, let's make an interesting angle. Let's do like pi over 4, halfway between. I think those are good step sizes. So let's say that we go by pi over 4s. So there's 0 and then 1 pi over 4. This is actually 2 of those pi over 4s. And this will be 3 pi over 4. And this will be 4 of those pi over 4s. And then 5 pi over 4. That is actually 6 pi over 4. Here's 7 pi over 4. And finally, that is 8 pi over 4. And if you recall, because we have special triangles going on, right? If you're facing an angle of pi over 4, then, and you have a unit circle there, then the x value is 1 over root 2, and the y value is 1 over root 2. So therefore, the y value is 1 over root 2. And if you face 3 pi over 4, the y value is again 1 over root 2. All right, sounds good. If you're facing 5 pi over 4, which is down here, your y value is a negative 1 over root 2. Again, from the special triangles. And finally, if you're facing 7 pi over 4, your y value is again negative 1 over root 2. Negative 1 over root 2. And there we go. So this gives us enough information to graph on the Cartesian coordinate system. Now you may say, well, didn't we graph it using the unit circle? And the answer to that is heck no. What we've done with the unit circle is we've found the y values, but we haven't actually graphed x versus y here, angle versus the y value. So graphing the angle versus the y value would be to graph this or plot these points. So let me go ahead and take a moment to cleanly draw out down below here a good Cartesian coordinate system. All right, there we have it. I've just drawn out this graph here, x versus y. And let's go ahead and plot the points. Those dots are just to help me plot those points evenly. Notice the y values. I went from negative 1 to 1, and that's because the outputs for the sine curve go from negative 1 to 1. Remember, they're the y values on the unit circle, and the y values go from negative 1 to 1. So this will guide us quite a bit. So let's see, I'll use a different color for graphing, maybe blue. All right, let's go ahead and plot 0, 0. So I'll go down here and plot 0.0. And let's see, pi over 4, comma 1 over root 2. Now 1 over root 2, you'd need a calculator to know exactly where that is, but it's roughly 7/10. So I'm gonna plot it maybe right here. And then I think that dot is massively large, but that'll work fine, I guess. And then pi over 2, we're at a height of 1. Something right there. 3 pi over 4, we're going to be at a height of 0.7 again, which is 1 over root 2. And at pi, we're going to be at 0. I'm just copying from this list, by the way. And then we go to the negative sides, right? Negative 1 over root 2, negative 1, negative 1 over root 2, and 0. So let's go ahead and plot those. Negative 1 over root 2 is probably about there. Negative 1 is probably about there. Negative 1 over root 2 again, and then back to 0. Now, I only plot these by hand just to showcase that it looks like the curve does this. I kind of missed there, I apologize, but such is life. And for those who know about sinusoidal motion, this is actually a good graph of the sine function. Now remember, our arguments for the sine can go negative too. In other words, I could have said I want to plug in angles going backwards, so negative angles. So our x value, our argument for the sine function here, could have been negative. In other words, coming back to this graph, I could have gone the opposite direction. Remember, the values should repeat, so they should go on forever. And we're going to prove that later on, or at least showcase it. So it goes forever in both directions. But the wonderful thing about knowing what this graph looks like is that you can quickly, once you know the base graph of this, and once you kind of memorize the shape of it, which is very easy, you can quickly evaluate the sine function at nice values. Maybe not pi over 4, but pi over 2, pi, 3 pi over 2, and 2 pi and 0. Very fast to use the graph here to help you evaluate trig functions. That's what we're going to be doing in the long run. Now let's go ahead and do the same thing, but for the cosine. I'll do it on this side over here. So we're going to let g of x equal cosine. So I've pre-done the table using the same inputs actually, because they're nice to use. And remember, the cosine is going to give me the x values in this graph. So I'm going to look at the unit circle and look for its x values. So let's, for example, talk about x equals, or sorry, the angle of 0. When you're facing the angle of 0, which is right here, your x value is 1. When you face the angle of pi over 2, which is right here, your x value is 0. Make that cleaner. When you're facing an angle of pi, your x value is a negative 1. So I'll just write that in. And when you're facing an x value, or sorry, an angle, that's what I mean to say, an angle of 3 pi over 2, that's what that is, your x value is 0. And again, when you're facing an angle of 2 pi, you're facing an angle of 0 again. And so your x value again is 1. In between, at the pi over 4 and 3 pi over 4 and 5 pi over 4 and 7 pi over 4 angles, at pi over 4, this angle right here, your x value is 1 over root 2. At 3 pi over 4, that's this angle right here, your x value is a negative 1 over root 2. At 5 pi over 4, right there, again, your x value is a negative 1 over root 2. And then finally, at 7 pi over 4, right here, your x value is a positive 1 over root 2 because you're in quadrant 4. X values are positive in quadrant 4. So there we go. Now, let's go ahead and plot these points. By the way, I kept saying x value, which is correct for the unit circle, but don't confuse that with this x right here. That's just what we're going to be using. We're going to graph on the xy axis. So x now is going to stand for our angle, and the y value is going to be our output for our cosine. So let's go ahead, zoom out here. And down below, I'm going to go ahead and right below this, I'll graph another Cartesian or an x-axis. All right, I got that laid out. Now let's go ahead and go back to our table here. Let's see, when x is 0, the y value will be 1, so I'll plot that. When x is pi over 4, y will be 1 over root 2, which is roughly a 0.7. So I'll just write that right there. When x is 2 pi, the y value is 0. When x is 3 pi over 4, the y value is a negative 1 over root 2. That's a negative 0.7, roughly. That's going to be kind of hard for me to plot by hand, but okay. When x is equal to pi, -1. And then I'll just go from memory from here. It's going to go through a -1 over root 2, a 0, a +1 over root 2, which I think is right about there, and then a 1. And if you connect these dots up, hopefully with somewhat of a smooth curve here, there we go, you get the cosine curve, which looks very similar to the sine curve. And actually it does go off in the other direction. It continues on forever and ever like that. They look incredibly similar, and they are. They're very similar curves, but the sine starts at 0, 0. Let me write that in. The sine starts at 0, 0. The cosine starts at 0, 1. Otherwise, they kind of have the same oscillation or the same picture. And in fact, because they are cofunctions, they should. Notice the cosine in green is shifted to the left pi over 2 units from the sine. The sine is shifted pi over 2 units from the cosine. So they are the same functions, just shifted. Now let's go ahead and go to this app here, because this is going to really help us get a great view of what's actually happening in the background. Now what you see is the unit circle. That's just the unit circle, and it's carving on there's a point that's kind of rotating around. Notice this point, it will have X and Y values as it rotates around. And what we're really concerned about is, what are the Y values? If I want to graph the sine, I want to graph the Y values that are being cut out by this rotating unit circle. So let's go ahead and turn on the sine graph right now. This is actually graphing the Y values as it rotates around. And notice it is actually graphing out our sine curve. And it'll keep going on forever and ever and ever. So this is a great animation of how the sine curve is made. And remember, the X values are all the cosine values. So if I were to look at all the X values for all these points, it would give me the values for the cosine. Now that is going to look a little bit different to you possibly. So let's see what happens when we graph the cosine here. I'm waiting for it to catch up. Boom. Okay, so now it's graphing the X values. The X value here is going to be -1, and then 0, and then the X values are going to be +1, and then the X values go to 0, and the X values go to -1. I'm looking actually right here, and then to 0, and then to +1. So that's, again, what it's doing is graphing out the X values as it goes through this. So it's a great visualization of the sine and cosine functions. I wonder if I can turn both on. Yes, I can. So there you go. You can see both at the same time. Now, as I've mentioned a few times here, the sine and cosines, they repeat their patterns, right? They repeat because everything's based on the unit circle. So all X values start repeating their pattern after a full rotation of 2 pi. And so that defines the period of both the sine and the cosine functions. And this is actually the true definition of what a period is in mathematics. For any function, y equals f of x. It doesn't have to be a trig function, just any function. The smallest possible number p for which f of x plus p is equal to f of x for all x in the domain is called the period of f of x. And really, to put that in language, it just means the smallest number p that we can find where a pattern starts to repeat. Like I said a moment ago, it doesn't need to be a trig function. You could have maybe a jigsaw pattern like this, a saw pattern that goes on forever and ever, ... right? And let's suppose that this was x equals 1, and this is x equals 3, and this is x equals 5, and 7, and 9. While somebody would say, and thank goodness for technology to help me describe this, somebody could easily say, you know what I'm going to do? I'm going to copy and paste the interval from 1 to 5. While that is true, you can copy and then paste the interval from 1 to 5 and paste forever and ever and ever, and it would create the pattern. That's not the smallest such interval you could have copied. you could have just copied the interval from 1 to 3. And so because that's the smallest such interval where the pattern begins its repetition, the period of this is going to be that distance between 1 and 3. So the period of this is equal to 2, because that's the length of the pattern that I'm copying. That's a distance of 2 right there. And so if you think about the sine curve, which we've just graphed, but it looks like this, and then it repeats from that point forward and backward technically, and that length was 2 pi, I can capture the entire pattern of the sine curve between 0 and 2 pi. So the length of the copy, the length of the snippet that I will copy there, is 2 pi. So the period here is equal to 2 pi. And the same thing with the cosine. The cosine, again, I just like to graph it because it's good to see it being graphed. The cosine starts high and goes low. So it does something like this. And it does that full pattern in a length of 2 pi. Halfway through would be pi. Half of that would be pi over 2. And so therefore this would be pi plus pi over 2 or 3 pi over 2. This is a height of 1. This is a depth of -1. The pattern will continue from that point forward and back. And all I need to do really to capture the entire information for that cosine curve is copy the pattern from 0 to 2 pi. So in other words, its period again is 2 pi. And that's what this theorem is just stating. That the periods of the sine and the cosine functions are 2 pi. And that is somewhat easy to understand just from the unit circle, also from our graphs. But that's going to become critical, so that's a very memorizable piece of information. So let's do the following by hand. Let's graph both the sine and the cosine on the interval -6 pi to +4 pi. And the way we're going to do this is we're going to graph basically from 0 to 2 pi first, and then copy and paste that interval. And I just start this process. I create a double set of axes here, one for the sine and one for the cosine. It's just a little bit easier for me. And we'll go ahead and plot out, because we know that the patterns are 2 pi periodic. I'll go ahead and label where 0 is 2 pi, 4 pi, -2 pi, -4 pi, and -6 pi. That will be very helpful for us. And you can see I made a bit of a mess, but that's only because of the fact that I want to know where the highest highs are and the lowest lows are. Let me label some of these. This height is 1, that depth is -1. This is going to be pi, 2 pi, 3 pi, and 4 pi. And same thing, -pi, -2 pi, and so on and so forth down the line. So let me go ahead and pause this. All right, we got that done. Let's go ahead and take care of the sine graph. The sine starts at 0, 0, and it climbs to a height of to a height of 1, and then back down to a height of 0 at time pi. So it's going to look something like this. I'll use blue again for this graph. So halfway between 0 and pi, it'll reach its apex. So it'll look something like this. Come back down. Halfway between pi and 2 pi, it'll reach its minimum. Halfway between 2 pi and 3 pi, it'll reach its maximum. And this is based, if you're wondering how I get that halfway between idea, it's because we plotted these points earlier, so I'm kind of using that information. We plotted that at pi over 2, the height for the sine was 1. And so, or the output for the sine, I should say. So this is the sine curve from 0 to 4 pi, but we want to go backwards as well. So I'm going to actually plot the halfway points here just to help me out really quickly. And you'll see that it's just much faster to plot the maximums and minimums to get things going. So there we go. Something like that. Make sure it meets up. These are not points, by the way. I will often see students who do this. Boop, boop. That is not true. It is a nice smooth curve throughout. You have to make it as such, if you can. I know they can look pointy, but they're not. They're a nice smooth curve throughout. And almost done here. I think when I do the cosine, I'll just pause for that piece. All right. So there is the graph of the sine from negative 6 pi to positive 4 pi. Now the cosine, on the other hand, which I'll draw in green, that, remember the x value is basically the same. That starts at 0, 1. This is a height of 1. This is a depth of negative 1. And then it dives down to 0, and then to negative 1, then to 0, then to positive 1. So it starts high, goes through the x-axis, goes low, and then climbs back high. So that's this first cycle, and ends at 2 pi. And then that cycle will continue. So it'll go down through the x-axis to negative 1, through the x-axis to positive 1. And again, you could plot values if you wanted to, or build a table, but that would get very abusive in a trig course because you're going to need to graph these super quickly. Although, to be honest with you, we do not normally graph in trig going from negative huge pi to positive huge pi. We generally go for a single cycle just to see what the base graph looks like. But this is just a heads up that you could be asked to do. Whoops, kind of messed up at the end. Sorry about that. My hand slipped. So there we go. Those are the graphs of the sine and cosine by hand from negative 6 pi to positive 4 pi. There you go. Now, since we just discussed the period of a function, it is kind of useful to use the period of the function to help evaluate a trig function. So we're going to take a moment to do an aside, a computational aside. Since we know the period of the cosine is 2 pi, and we're being asked to evaluate the cosine of negative 19 pi over 6, we know that this should be the same as the cosine of negative 19 pi over 6 plus 2 pi. Now remember, 2 pi is 12 pi over 6, so that would be the cosine of negative, let's see, negative 19 plus 12 is negative 7 pi over 6. And if you do not like negative angles, you could add another 2 pi to that if you want to. And of course, you do not need to actually write out all these extra little additions. You could have from the get-go said, you know what, I'm just going to add maybe 4 pi to this. And you could have quickly got to the point we're about to be at. Negative 7 pi over 6 plus 12 pi over 6 is a 5 pi over 6. And now we're ready to go if you like positive angles. So cosine of 5 pi over 6, we talked about reference angles in the past, so this is sort of like the cosine of regular old pi over 6, with the exception that 5 pi over 6 as a rotation ends in quadrant 2. And all students take calculus. Cosine is not positive in quadrant 2. Cosine is negative in quadrant 2. So this is a negative cosine of the reference angle of pi over 6. And I will go ahead and draw out my pi over 6, pi over 2 right angle triangle. Pi over 6, pi over 3, sorry. 1, 2, root 3. And cosine of pi over 6 is adjacent over hypotenuse, root 3 over 2. So the answer will be a negative, because quadrant 2, root 3 over 2. So that's using the period to help you evaluate a trigonometric function. Do you need to? No. But it is sometimes very helpful to do that, rather than to say, oh, well, let's see, I'm going to rotate how many times through and end up here, right? It's just much more useful to just say, let me add a couple sets of 2 pi so that I can graph, so I can find the reference angle quickly and the quadrant quickly. Now, here we go. Cosine of pi over 2, sine of pi, cosine of 0, and sine of negative pi over 2. Use the graphs to evaluate this. And this is actually what you're going to be doing. You're going to be referencing the graphs to help you plot these or evaluate these functions rather than using triangles when you land at quadrantal angles or axial angles. So all these angles end on an axis. And so that's when the graph becomes incredibly helpful. And by the way, when I say land on an axis, I mean when you rotate through an angle, right? So that's the angle of pi over 2. This is the angle of pi. Here's the angle of 3 pi over 2. So that's what I mean by when you land on an axis. So let's go ahead and go back to our very first by hand graph and evaluate these functions. Actually, I kind of changed my mind on that. I would rather just regraph them. So the sine function starts at 0, 0. It oscillates like this. It goes through that full oscillation in a period of 2 pi. Halfway through that period is pi. Half of that is pi over 2. So this point would be pi plus pi over 2 or 3 pi over 2. Those are called our key points, by the way. And this is, again, sine of x. That's the sine function. So, and down below, I'll go ahead and graph the cosine function. Cosine starts at, I didn't label these heights here, 1, -1. Cosine starts at a height of 1, and then it just goes through the same process. Notice I'm kind of chicken scratching it out. I'm not really being super exact here. The reason why is because I don't need to be when I'm just evaluating. I just need to get a good idea of what the graph sort of looks like. So I get these points labeled and watch what happens. Somebody asks, what's the cosine of pi over 2? If I have this graph in my brain already, I know its output is 0. You plug in pi over 2 into the cosine, you get an output of 0. How about the sine of pi? Again, if I know the sine graph, sine of pi is 0. How about the cosine of 0? Well, if I know the cosine graph, the cosine when I plug in 0 has an output of 1. Sine of negative pi over 2. Notice that's not on this graph, but I could actually just go back a little bit to a negative pi over 2, and I see the output is a -1. And this brings up a really important point here, that these functions have odd and even identities associated with them. You should recall that sine is odd and cosine is an even function. And so even functions are symmetric about the y-axis. Odd functions are symmetric about the origin. In other words, they can be rotated 180 degrees and look exactly the same. Well, if sine is odd, that means sine of negative pi over 2 is the opposite of sine of pi over 2. And sine of pi over 2 is 1. Thus, sine of negative pi over 2 is negative and then 1. And I could do this all day long, right? So the cosine of, let's say, a negative pi. Since cosine is even, it's the cosine of pi, and now I can just look at my regular cosine graph and say, oh, cosine of pi is -1. So this is how you would evaluate a trig function using its graph. Only if your angle that you're evaluating the trig function at lands on an axis. In summary, I just want to round up the things that we know about the sine and the cosine functions so far. Besides their graph, right? Their graphs, we know. The sine and the cosine have the domain of all real numbers. In other words, they oscillate forever in both directions. They bounce between -1 and 1 as far as their outputs. So their range is -1 to 1 inclusive. So it includes the edges. And the period for both of those functions is 2 pi. The cosine is an even function and the sine is an odd function. Those are all critical pieces to remember as we move forward. All right, that's enough for this video, I think. And so what we're gonna do is come back in a little bit. In the next video, we'll do amplitude and reflections, basically start our transformations of the sine and cosine function graphs.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles. obstacles getting in our way cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.